Okay, well, today's the last day of numerical integration, and it's really one of my favorite topics of the whole semester. This one also plays a role in my reading, plus I just think it's cool stuff. Okay, Gauss Quadrature. So far we've seen interpolatory quadrature, such as Newton codes that can use equal space nodes, but that can go badly. Use too many of them. And then we've also seen composite rules, and those are certainly an improvement, but they make the unnecessarily computation expensive, at least for certain intervals. So Gauss Quadrature is going to be an attempt to do better by realizing greater accuracy and efficiency. So I'm going to bring back a concept from early on in the chapter, the degree of accuracy. So if you have an interpolatory quadrature rule, such as the Newton codes rule, the degree of accuracy is the highest degree of polynomial that it will be integrated exactly using that interpolatory rule. Now, as I mentioned before when I first introduced degree, if you have an n-node interpolatory quadrature rule, and just to refresh your memory, that's where we'll be approximate your integrand by the interpolated polynomial, where you're interpolating at the nodes, and you integrate the polynomial exactly. So the degree of accuracy is at least n minus 1. But we already have seen examples where it can be higher than that. Because Simpson's rule, for instance, uses 3 nodes, and so the degree is at least 2, but it turns out to be 3. So what we want to look into today is what's the maximum possible degree that we can get if you have n nodes. What is the number bound on the degree for that n node rule? So we have a general quadrature rule. So we have a sum of your integrand evaluated at your chosen nodes, whatever they may be, and then multiplied by these weights. Then your quadrature rule is defined completely by 2 n parameters. You have your n nodes, and you have the n weights that go with them. So since we have 2n total degrees of freedom, maybe we can use that flexibility to get a higher degree than what we've seen so far. So one approach that we can use to try to get a rule like that is called direct construction. So the idea is you set up a system of equations for your nodes and the weights. So the nodes and weights are unknown at this point. And we're going to require that the quadrature rule applied to the integrand x to the j is exact for all powers of x, j, going from 0 up to 2n minus 1. Now, the reason why I have this range of j values going from 0 to 2n minus 1, that's 2n equations in total that go with the 2n parameters we have. Because normally, if you have 2n degrees of freedom, you can only impose at most 2n equations, and hopefully those 2n equations will determine a unique solution. So if we can solve this system, then because the quadrature rule would handle all of these integrals exactly, then we can say that this quadrature rule has degree of accuracy 2n minus 1. So you might think, okay, no problem. We'll just go ahead and solve this, and we have our maximal degree quadrature rule. But here's the problem. This is a nonlinear system of equations. This isn't one of those cases where you can apply row operations, do elimination, substitution, and you're done. It's a whole lot nastier than that. With that, against that backdrop, I've assigned you the n equals 2 case for homework. So that'd be part of homework 8. And this is where I remind you that you can drop certain assignments. Okay. I mean, yeah, n equals 2 case. So we're talking 4 equations for 4 unknowns, right? It's not too terrible. It's doable. Students have done it. But beyond that, it would be fairly awful, and I would not assign something like that. Okay. So the point is, and because we want to be able to do this for whatever value that we have, so it's worth asking: is there an easier way to get a quadrature rule of maximum possible degree than solving this system of nonlinear equations? Because with linear systems of linear equations, there's a whole lot of theory that you learn about in Math 326. As to when does it have a unique solution, when does it have a solution at all? That theory doesn't necessarily carry over to systems of nonlinear equations. It's a whole lot more difficult to determine if a given system of nonlinear equations even has a solution, whether it's let alone being unique or having a way to get it. For those of you who go on to the next semester, which are many of you, a few were proud, that is something that we will look into at that point. All right, so different approach. Using the wonderful concept of orthogonality. Now, you all have seen orthogonality before, certainly in Cal 3. So where it comes up in that class, well, I talked to some of you last semester, but I'll see you again next semester. Yay. So in Cal 3, you learn about how 2 vectors, ordinary vectors, in like R2 or R3 are orthogonal if their dot product is equal to 0. Now, we're going to apply the concept of orthogonality to functions of x. So we say that 2 functions are orthogonal if their inner product, which is the integral of f times g, is equal to 0. Now, it's important to recognize a parallel between this notion of orthogonality for vectors in R3 versus this notion of orthogonality for functions of x. Because in the case of the dot product for R3, you're multiplying corresponding coordinates and adding them all up. Well, that's what's kind of happening with an integral too. You're multiplying corresponding components, in other words, f and g evaluated at the same x. If you think of the integral as a limit of a Riemann sum, the Riemann sum for this integral would literally be a dot product. So it's think of as an infinite version of this. Now, there are all kinds of inner products in this form. We can choose any interval AB. A lot of inner products have have an integral. It might have a positive weight function included. So there are literally infinitely many possible inner products in this form. But we'll stick with a generic one of some interval AB. I should mention I have to be very careful here and point out these are real valued functions. If f and g were allowed to be complex, then one of these functions, usually the one on the left, would have to take the complex conjugate. But for this inner product to be defined properly. But we don't need to worry about that here. We can stick with everything being real. Okay. Now, it can be shown, I won't go through the whole thing here, but that it's possible to construct a sequence of orthogonal polynomials, Q0, Q1, Q2, and so on, up to whatever degree you like, that have these properties. So Q sub j has degree j, so Q0 is a constant, Q1 is a linear function, Q2 is a quadratic, and so on. And the inner product of any two of these polynomials is equal to 0 if the indices are not equal and equal to 1, the inner product is equal to 1 if they are equal. And the terminology for that is okay. So these polynomials can be normalized so that they are not just orthogonal, but orthonormal. So let's see that polynomials like this, they're orthogonal if the inner product of any two distinct ones is 0. But if the inner product of one of these with itself is also equal to 1, then they're orthonormal. This is similar to like if you have vectors in Rn. If a dot product of any two distinct vectors is 0, but the inner product of any vector of itself is 1. In other words, vectors of unit length, that's a unit vector, then that's a set of orthonormal vectors. Questions so far about the whole idea behind orthogonal functions? I mean, it's probably something pretty weird for y'all. Yes.
So yeah, let's say if back to the inner product, if f and j, at least one of them is a complex function.
Yeah.
Now, one of them. So does it matter which one of them is conjugated?
Not really, but it's just important to define it in a consistent way for whatever you're doing.
Okay.
Most books I've seen will say that the left operand of the inner product is the one that gets conjugated.
Like a convention thing?
Yeah.
And that is to ensure that the answer is real.
It's to ensure that the inner product of any function with itself is a non-negative real number. So that way it's a magnitude.
Is this the class you're supposed to learn inner product?
Wait, is it class?
Yeah.
Well, I never thought about it that way. I mean, yeah, you saw it in number class.
Yeah. So,
Before 15, but yeah, I'm trying to think of like whatever classes does, because you see dot products in calculus, but as far as like inner products beyond that, I think they only come up in here and in 415. Okay.
I didn't know if there was another, like, because I know it from that, so.
The only other class I think they might come in is linear algebra 2, which is math 426, which is only sporadically offered. So, yeah, because I know orthogonality is covered there, but I don't know how far I go with it.
Just seems like a lot of place put inner product in the class. I guess at least more learning it here. It seems like it's more of a fundamental thing, someone else.
Oh, that should have come up before now?
Yeah.
Yeah, I won't disagree with that.
Yeah. Okay. Sounds great.
Okay. Now, so here's some specific examples of orthogonal polynomials. So, for instance, if you have the interval -1 to 1, so A and B are -1 and 1, then your orthogonal polynomials on that interval are called Legendre polynomials. And the Legendre polynomials, they're not orthonormal, they're just orthogonal. So the inner product of these is equal to 0 for I not equal to j, but the inner product of itself is not equal to 1. I think it's something like 2 over or 2 equals 1, something like that. There's a formula for it. Okay, so this is one of the best known families of orthogonal polynomials. But another example is one we've actually seen before, the Chebyshev polynomials from polynomial interpolation. So they are orthogonal in this sense. Still the interval -1 to 1, but the difference compared to the Legendre polynomials is the inner product is defined to have, I mentioned this a few minutes ago, a weight function. So the inner product of f and g is f of x times g of x times this weight function, which notice it's actually undefined at the endpoints, but at least it's defined in the interior, so it's okay to use the weight function. Now, you may remember from homework, I'm not sure which homework it was, might have been homework 5. One had Chebyshev problems on it. One of the problems for that assignment was you had to prove a 3-term recurrence relation for the Chebyshev polynomials, that each one depended on the previous 2. And notice here too, algebraic polynomials, each one depends on the previous 2. That's actually a property of all families of orthogonal polynomials. They all satisfy a 3-term recurrence relation, which is quite convenient for generating them. I'll also make a note here that in the textbook, we don't cover this section in this class, but I have a more in-depth treatment about orthogonal polynomials. If you're interested, in section 8.2. And I think it's actually proven there. I can't remember like if I prove myself in the book or if it's like assigned as a problem. And when feeling illness that day, you're proving that all families of orthogonal polynomials satisfy this kind of recurrence. Okay, now it's all fine and dandy about orthogonal polynomials, but I haven't explained how they help us getting a nice, effective quadrature. But I'll do that now. Okay, so we're going to assume that our integrand, f of x, actually is a polynomial degree less than 2n. So the goal is to come up with a quadrature rule that's guaranteed integrated exactly, even though it's only using n nodes. So we want the exact integral of f of x to be equal to this quadrature rule, but that in turn is equal to the exact integral of its interpolating polynomial. So we have these nodes, x1 to xn, which I've not told you what they are yet. And Pn minus 1 interpolates f at those nodes. Let's take a look at the error. So the error would be the integral of f minus the interpolating polynomial. Now keep in mind, this is a polynomial up to degree 2n minus 1. This is a interpolating polynomial up to degree n minus 1. So the difference between these two is also a polynomial of degree up to 2n minus 1. Now, I can actually factor this to a point, because f and Pn minus 1 are in agreement at the nodes. So, since the error is equal to 0 at the nodes, I have this part of their factorization. Since I know that this polynomial is equal to 0 there. Now, the polynomial as a whole is degree up to 2n minus 1. If I take these n factors out, I have this remaining. So r for remainder. So this polynomial is everything else that's in the error, and its degree at most n minus 1. So here's how orthogonality helps. Suppose I choose my nodes, x1 up to xn, to be the roots of this polynomial, qn of x, which is chosen to be orthogonal to previous orthogonal polynomials, q0, q1 up to qn minus 1. Now, because qn is designed to be orthogonal to these, all of them, it'll automatically be orthogonal to all linear combinations of them. In other words, Qn of x is not just orthogonal to these, it's orthogonal to all polynomials of lesser degree. Now, since x1, x2 up to xn are for roots of Qn, then I know that Qn has this kind of factorization. It's equal to the product of all these linear factors times some scaling constant that I don't really care about. This is something that's actually this is proven in chapter 8, that it can be shown that the roots are real, distinct, and they lie in the interval AB. This is something that you were assigned to prove specifically for Chebyshev polynomials, that a Chebyshev polynomial of whatever degree has roots that are real, distinct, and lie in the interval -1 to 1. So that's a property that actually applies to all families of orthogonal polynomials on whatever interval they're defined. So now let's take a look at the error again. So earlier, I got the error down to this point. But the error is equal to the integral of this polynomial times this one. But that can be described as an inner product of Qn with the remainder part of the error. This is of degree n. This is of lesser degree. Qn is orthogonal to all polynomials of lesser degree. Therefore, this inner product is 0. But the inner product is the error, so the error is 0. In other words, the quadrature rule is exact for all polynomials of degree up to 2n minus 1. So even though there's only n nodes. Any questions about how this error turned out to be 0? Yeah.
So, okay, you've got f of x, you've got that interpolant p of degree n-1. You subtract those, you get error of that form.
Yeah.
And then you're able to find an orthogonal polynomial Qn of x that would have those x1 through xn as its roots.
Yeah.
You're able to find that.
Yeah.
And it can be proved.
Okay. All right. So, as far as there's a lot going on here. Okay, because they're gonna say, oh yeah, suppose we choose these to be roots of this polynomial that does this. Okay. Now, there is an actual algorithm for generating orthogonal polynomials. So if you specify, like, I want them orthogonal on this interval AB, and if there's a need for a weight function, here's a weight function. But in this case, weight function would just be 1. That uses a 3-term recurrence relation to systematically generate orthogonal polynomials up to whatever degree.
So there's an algorithm that helps us construct.
Yes. I have not stated the algorithm here, nor will I.
Is it a question?
What?
Is it a homework question?
No. Not feeling that evil. No. So I'm going to emphasize, we are very much just tiptoeing into this, because that's enough suffering for an undergraduate as it is. Okay. Because, all right. Because, for example, if I look at the Davis recurrence relation for genre polynomials, well, how are these constants figured out? You know, and there's also a similar recurrence relation for Chebyshev polynomials. Now, that one was easy to get because you can use trig identities. But in a general case, there are integrals to work out. of polynomials to make all that happen. And it is something that I could write out. And I think actually, let me check, because I have it open anyway. Yeah, there's a description for orthogonal polynomials. Oh, okay. Well, it's based on something you may be familiar with, the Grant-Schmidt orthogonalization process. But as applied to, here it is. So all orthogonal polynomials have by recurrence relation to this form, the three-term recurrence relation. And here are the formulas for the coefficients. We see these coefficients alphas here and betas here. So that's known. Okay. So that can be used to generate them. Now, but then, let's suppose you use that and you have your orthogonal polynomial. Still gotta get the roots. That could be a pain. Now, in the next chapter, starting in the next class, I'll be talking about methods for finding roots of functions. But I showed you like the function for computing roots of a polynomial in MATLAB can go unstable for certain polynomials. Now, it can be shown, and it definitely won't get into this here because that the task of computing the nodes, the roots of this polynomial, can be described as finding the eigenvalues of a symmetric tridiagonal matrix, which is actually a very nice problem to solve. It's pretty well behaved and can be solved efficiently. So, and it was actually my advisor who did a lot of work on that area. And the eigenvectors can be weights. So, okay. Now, the reason why now, we're not getting into all that here in this class. So really we're kind of settling. And I might not like that, but here's what we can do, even without getting into all that. Because anyway, so first, getting these nodes and the weights that go with them. Now, the weights are just interpolatory weights. I mentioned previously the interpolatory quadrature. The weights are the integrals of Lagrange polynomials. That's still true here. And this is interpolatory quadrature still. It's just with specially chosen nodes. And so those nodes and weights together make what's called a Gauss, or sometimes referred to as Gaussian quadrature rule. Now, if your interval is -1 to 1, then you have Lagrange polynomials. But if you're on a different interval, AB, you could take the Gauss quadrature nodes and weights for the Lagrange polynomials from -1 to 1, and you can do a simple linear mapping. So this formula right here takes x values that are in the interval -1 to 1 and does scaling and shifting to map those values into the interval AB. So you can take your nodes for -1 to 1 and get nodes for AB just doing this. So to get the Gauss quadrature nodes for the interval -1 to 1, you can look them up, and I can show you that. Okay, so we made a Gaussian quadrature, whatever. Okay, yeah, here are tables of nodes up to degree 5, and using radicals, so you have formulas for exact values. And kudos to whoever worked all this crap out. and here are the weights that go with them. Now this is just up to 5, but if you want a higher degree, you can find them online to machine precision, like 15, 16 decimal places. In other words, format long. Now these would always be for -1 to 1, and then you map them to whatever interval you are working with. Now the weights, okay, as I mentioned earlier, there are the integrals of Lagrange polynomials. But what's interesting is it can be shown that they're also equal to the integrals of Lagrange polynomials squared. Now, the integral of a function is generally not equal to the integral of its own square. But that is true for Lagrange polynomials for these points and only these points. Now, this is important to know because it proves that the weights are strictly positive. And that's something we really like because I mentioned earlier Newton-Cotes rules. If you use equally spaced nodes for Newton-Cotes, once you have too many of them, you're going to have negative weights, and the quadrature rule is unstable. So Gauss Quadrature rules are always numerically stable. So high degree of accuracy, good numerical stability, can't beat that. And because the weights are guaranteed positive, and it can be proven that as n goes to infinity, the Gauss Quadrature approximation integral converges to the exact interval. If you want the weights for an interval AB, what you can do is you can use a table like I just showed you to get the weights for -1 to 1. I should make clear it's from -1 to 1. So for a general interval AB, you just multiply them by b minus a over 2. So for nodes, you scale and you shift. For the weights, you just scale by the same factor. So the question about getting nodes and weights using a table. That's all I could homework. Yes.
So if you scroll down a little bit, a little more. That's Gaussian function?
Yes.
Is it like, okay, never mind.
Is it related or something?
No.
Okay.
The interval of integration.
Yeah.
y0 to 1 specifically, like you just say for the sake of simplicity, or it has
Just a fun example.
Alright.
Yeah. Actually, it's an example from the numerical analysis textbook that I first learned from, which I'm counting before in 1988.
Oh, nostalgic. Nostalgic.
Yes, it is. Okay. All right. So because I can't help myself, I just think it's really weird that the integral of the function is equal to the integral of its own square. So I was like, okay, prove it. Well, I'll prove it. So if I consider this, I want to show that this is equal to 0. Now, a Lagrange polynomial is in degree n minus 1. So square would be degree 2n minus 2. So because this whole thing is degree 2n minus 2, the Gauss quadrature rule can integrate this exactly. So I can say that the integral of this difference is equal to the quadrature rule applied to this integrand, which would be evaluating these Lagrange polynomial and its square. Oh, okay. At the nodes, but remember, Lagrange polynomials at their own points are always equal to 0 or 1. And that's certainly true of a square also, because 0 and 1 squared are 0 and 1. This whole thing is 0. Each of these terms in square brackets is 0. So the whole thing is 0. Now, So that's an example of how effective Gauss Quadrature rules are compared to other ones that we've seen. So we have integral Gaussian function from 0 to 1, something that must be evaluated numerically. So let's suppose I want to use certain rules with enough nodes to get 8 digits of accuracy. So if I use a composite trapezoidal rule, which I mentioned earlier is the best rule to use for periodic functions, but for something non-periodic like this, it's not so great. It takes 2,500 trapezoids to get 8 digits of accuracy for this. So that's pretty awful. Now, if I change to composite Simpson's rule, which is 4th order accurate, a whole lot better. But for just the integral of a smooth function from 0 to 1, it seems still like excessive. But Gauss Quadrature does a whole lot better. So this is why Gauss rules are very often used in like professional mathematical software. Now, there are integrands for which Gauss Quadrature might not be the best, but that's why there's all kinds of add-ons to these, like additivity and so forth, and various ways of getting error estimates and so on. But in terms of efficiency, it's not too often where you get something really striking like this, but you can do so much better. That's why it's important to know about. Okay. Any questions up to this point? Sorry. Okay. First, error analysis is concerned. So normally what you do for a quadrature rule is you take the integral of the interpolation error. So Pn minus 1 is the Lagrange interpolated polynomial of degree n minus 1. But we're going to take a different approach here with Gauss Quadrature. Is the error formula. Okay, we're actually going to use the Hermite interpolated polynomial. So remember, refresh your memory, this from like section 7.5. The Hermite interpolated polynomial matches your function that you're approximating at the interpolation points, but it also matches the first derivative at all of those points. So in this case, we have n nodes. So we're going to have, we have to match f of x and f prime of x at those n nodes. So you're going to have a total of 2n conditions. So your Hermite interpolated polynomial is going to have degree 2n minus 1. Now, okay. I'm going to show you this in the text. Okay. Okay. So I'll refresh your memory about Hermite interpolation. That this is one way of expressing the Hermite interpolated polynomial as a sum involving f values and f prime values. So it might seem strange that I'm getting the error in Gauss Quadrature by using a Hermite interpolated polynomial that requires values of f and f prime, because I'm certainly not going to use values of f prime in my approximate integral. But you'll see why this is actually a good idea. Okay. Now, again, to refresh your memory from Hermite interpolation, these are the formulas that were obtained for these strange polynomials of the fancy h's and the fancy k's. I want to check which problems of this section did I assign? Number 1 and number 5. Okay, so not this one. Okay. So if I take the integral of the Hermite Bernoulli polynomial, then I get this right here, which is the sum of my f values of the integrals of fancy h's. I'm going to have the sum of my f prime values times the integrals of fancy k's. But it can be shown, this is a problem that I did not assign, that because we're dealing with nodes that are roots from orthogonal polynomials, these integrals right here are 0. So in fact, and it can also be shown that the integrals of these fancy h's right here are actually the same as the integrals of the Lagrange polynomial squared, which I previously mentioned are the weights. So it turns out that the integral of the Hermite interpolating polynomial is equal to the Gauss Quadrature rule. So if I want to get the error in the Gauss Quadrature rule, then I can use the error from the Hermite interpolating polynomial, not the Lagrange one. And that leads to this error formula here. Because if I had used the error in the Lagrange interpolating polynomial, I would not get this error formula. I would get one that was incomplete. That really wouldn't tell the whole story of the accuracy of Gauss Quadrature. So that's why Hermite is being used. And it's actually one of the homework problems to prove this theorem. There's actually not a whole lot to prove, so don't worry about that. But because you're relying on interpolation error for the Hermite case. Oh, yeah, this problem right here is one that you want to do. Okay. Because if I use the error in Lagrange interpolating polynomial, I would get a formula like this, but the difference would be these would not be squared, and I'd have f nth derivative rather than 2n. And that would conceal the fact that the Gauss Quadrature rule is exact for polynomials up to degree 2n minus 1. Here, that's more apparent because if that is a polynomial of degree up to 2n minus 1, its 2n derivative is 0. So then the rule would have to be exact. But we wouldn't be able to see that unless we use the Hermite interpolation error instead of Lagrange. So again, it seemed like an odd choice, but thankfully everything worked out. I want to mention this. I've already pointed you to this section that's about Lagrange orthogonal polynomials, chapter 8. Somewhere in here. Okay, it's toward the end of the section. Yeah, this section right here. Roots of orthogonal polynomials. Here I have a proof that if I have orthogonal polynomials defined on interval AB, that they are roots are real, distinct, and they lie within the open interval of AB. I've actually seen some proofs of this in other textbooks, and I wanted to have original proof, so I came up with one. Okay, so if I come here to the notes. Oh, yeah, I guess you know better than I do. Okay, so in this class, and we keep things simpler in that and take a look at what problems I assigned plus, I saw one of them, error analysis. The other one I assigned from this topic, oh, this one right here. So the irony is, I don't give you any problems where you use Gauss Quadrature, except on the take-home final, where there would be like evaluate a certain integral using Gauss Quadrature rule, a certain number of nodes, and you're provided with the table of nodes and weights for -1 to 1, but you have to map them to your interval and so forth. So, yeah. So mathematically, something most interesting, but okay. Get your calculator or MATLAB or whatever. Okay, but yes, so the homework you do for this section is direct construction for the case of n equals 2, and you can use the table of Gauss Quadrature nodes and weights to see what you're supposed to get. But I will look at your work, so that you can't just do a bunch of algebra to write the answer. And then the one about error analysis. So, okay, but it's because of Gauss Quadrature's high degree of accuracy and their numerical stability of having positive weights that Gauss Quadrature plays a fundamental role in my research program. And it's actually based on some work that my advisor did. Some of his most important papers were from things related to Gauss Quadrature for certain problems from numerical linear algebra. And so I exported all that to PDEs. Let's see. I don't know if I have it. Oh, yeah, this is. That's what the Google Books page. Fine, whatever. Yeah, but this is a book that he did. Actually, it was his co-author who completed the book after Gene himself, who was my advisor, a couple years after he passed away. So it has all the gory details about things done with Gauss Quadrature, mostly for numerically inoperative problems, but for certain other applications too. And I don't know if there's I was hoping there'd be like a table of contents or something.
So that's the end of the.
Just about, hold on a second. Let's confirm with that. Usually you have to look inside or something. Oh. Okay, I guess I don't. Alright, anyway. Yeah, bugs been couldn't find it. My research actually has a section in that book. Section 11.7. I didn't even know about it. I would book was published. I wrote comments. I think you love subspace vector methods, but that's my stuff. If someone else had that do that, and I looked like, oh, that's fine. So I know I didn't talk about it. Okay, yes, we're done for real.
Now I'm ready to play.
Okay, I'll stop recording.